Hello, I'm Chance Hattrick, and this is my first short ISP, the Wheatstone thermometer. And so the purpose of the Wheatstone thermometer is to both display the temperature as well as determine if the temperature is above 20 degrees Celsius. So as you can see here, currently my thermometer is reading 19 degrees Celsius. I can increase the temperature by holding the thermistor, and at about 20 degrees Celsius, this LED turns on, indicating that it's above. And if the temperature were to be negative, then this red LED would turn on. And so there are two primary components of this circuit. We have the Wheatstone bridge with the operational amplifier as a comparator, and we have the Arduino Nano with the 7-segment displays. And so each of them have their own different ideas, and they have their own different uses. So the first part of this circuit is the Wheatstone bridge. The Wheatstone bridge contains the actual temperature reader of the circuit, which is called a thermistor. A thermistor is a device that changes its resistance based on the temperature around it. In my case, I am using a negative temperature coefficient thermistor, which is a thermistor that increases its resistance as the temperature decreases. And so when I hold my hand here, the resistance decreases in the thermistor. And so that is being used in this Wheatstone bridge. So the thermistor is used in a special circuit called a Wheatstone bridge. The Wheatstone bridge is a component that allows you to determine an unknown resistance based on 3 known resistors. It functions similarly to a parallel circuit with 2 resistors on each side of the bridge. The bridge consists of 4 resistors: our thermistor, a 2.2 k ohm, a 5.1 k ohm, and a 10.2 k ohm resistor. Despite its configuration, you can see these resistors are not in parallel because we have something connected in the middle. This could be a voltage reader, or it could just be another resistor. An interesting concept of the Wheatstone bridge is the voltage or signal difference in the center of the Wheatstone bridge. When the voltages at point D and point C are equivalent, then there is no voltage going through VG. And so we have no current in the center of the Wheatstone bridge. And this is called a balanced Wheatstone bridge. When the difference is 0, that's what we call a balanced Wheatstone bridge. So how can we tell if the Wheatstone bridge is balanced or not? Well, this is based off of the ratios of the resistors here. So for example, we could have a 5K, a 10K, and a 1K and a 2K ohm resistor. And because the resistance ratios are the same on either side, the voltage drop is also the same. As we know, resistors are akin to dropping voltage, and so the voltage drop at Rx and R1 will be equivalent, which will give us equivalent voltage at points C and D. And so that's how we get a balanced resistance, a balanced Wheatstone bridge. And this is very useful for finding an unknown resistance based off of the relationship here and with the ratios on either side. The Wheatstone bridge is connected to a 741 operational amplifier, with point D being connected at this pin and point C being connected at this pin. So when an op-amp is in comparator mode, then it takes its inputs and gives the output that has the highest, from the input that has the highest current. So when the temperature is low, the thermistor has a higher resistance, and so therefore it has a lower amount of current. And because of this, VD becomes our output, our inverting input, but because our negative voltage is connected to the ground, our LED is off when the temperature is cold. When we begin to heat up at, say, around 20 degrees Celsius, well, then at that point, the thermistor's resistance has decreased enough that its current is now more than point D, which would make our non-inverting input, or VC, our output. And this would turn the LED on. The next part of the circuit is the 7-segment display. In this part, the software of the circuit reads the voltage between the thermistor and this resistor, takes that voltage to find the resistance of the thermistor based on a known resistance of the 2.2 k ohm resistor, and then uses that resistance in order to find the temperature, because remember, the thermistor changes its resistance based off of the temperature. And so we use our known resistance to the thermistor along with the Steinhardt coefficients in order to find the temperature in the room. Now you may notice that this temperature will not be entirely accurate. And this is because of one simple reason: the Steinhardt coefficients. Every Steinhardt coefficient is different for every thermistor, and this is because the thermistor's change in resistance based off of temperature is a nonlinear relationship. It is exponential. And so whenever you use a new thermistor, you need to find the new Steinhardt coefficients. And this would involve exactly calibrating the thermistor with exact temperatures and exact resistances. And now, while this is not possible with my current resources, I instead used a program with approximate values in order to find a set of Steinhardt coefficients, which gave me something relatively close to the actual temperature. And so the circuit still works relatively well, but it's important to note that it will not be accurate unless you have the exact Steinhardt coefficients. And so as you can see here, when I warm up the thermistor, the temperature increases. And in our previous part of the circuit, the LED turns on because the current is now greater on the point C than it is on point D.